Welcome to Robotomy, where we supplant brains with bots. In this video, we're going to train bots to land spaceships on the moon. Hey everyone, it's Downer here with my friend and highly esteemed colleague, Chipper. Chipper, say something to the camera.
Hey.
That's what I'm talking about. If you're new here, subscribe and become a robotomist so you can follow us as we use deep learning to do dope stuff. Also, show Chipper you care and leave a thumbs up for his enthusiasm. Now, as is a long-standing tradition here on Robotomy, we're going to be using PyTorch and Jim to teach a bot to fly a spacecraft, and it's going to be the cat's pajamas. If you're unfamiliar, PyTorch is an open-source deep learning framework primarily developed by Facebook's Artificial Intelligence Research Lab. Its first stable release was in January of this year, but despite its youth, it's a growing juggernaut for deep learning applications. Similarly, Jim's also an open source library, but developed by the OpenAI Research Laboratory. Jim makes it easy to test various reinforcement learning algorithms and AI in a suite of standard environments, which you can just think of as game worlds. So in this video, we're going to use PyTorch to obliterate, and I mean wreck, a simple game environment in Jim. So, let's take a quick journey to a little place we like to call outer space. Chipper, hit him with the details.
Pack your bags and slap on that fairly uncomfortable astronaut helmet buried in the back of your closet, cause we're heading to the moon. The OpenAI Gym environment we'll navigate in this video is the so-called Lunar Lander. Now, it's a well-kept secret that the word lunar is derived from the Latin word luna, which means moon. It's also uncommon knowledge that, back in 1969, a small group of extraterrestrial travel enthusiasts paid a quick visit to the moon. And just in time to celebrate the 50th anniversary of the moon landing, our mission is to ensure...
Chipper, we actually missed the anniversary by about, 9 months. The 50th anniversary was in July of 2019.
Even better. Just in time for the 51st anniversary of the moon landing, our mission is to ensure our spacecraft can touch down in the right spot as quickly as possible. Like our forefathers, assuming we somehow manage to touch down in one piece, we can go for a quick moon stroll and maybe an ice cream cone to watch the sunset.
The lunar lander has 3 flight control mechanisms. It can rocket boost left, right, or up with the option of turning off all thrusters. And the objective is to land the rocket between the little flaggies as quickly and smoothly as possible for an optimal score. The environment tracks the elapsed time as well as the vertical landing velocity of the aircraft, along with a couple other key variables. So the best performances are going to look and feel like a frozen key lime pie to the face on a scorching hot day, light and refreshing. More details on the scoring system for this environment can be found on the Gym website. Links will be in the description. In this video, we're going to be testing 2 methods of training deep neural networks to navigate this lunar lander environment. These reinforcement learning or RL techniques, known as the cross-entropy method and Q-learning, offer distinct advantages and disadvantages.
A quick intuitive description of the cross-entropy method. Suppose you have a goldfish named Horace who's practicing his high dive routine. More than anything else, even more than eating fish food, Horace wants to dive in the Olympics, and he desperately needs your help. You agree to help by video recording his dives, being sure to take notes on his technique and providing a score on how well he executed each dive. At the end of each training day, you sort the footage from all the dives and hand to Horace the best ones to review that evening so that he can imitate the same technique the next day. You repeat this filming and scoring procedure until Horace can pull off a triple rotation quadruple gainer with no splash and becomes a 7-time gold medalist and national hero. Horace, we're all indebted to you and applaud the commitment you've shown to your craft and country. Thank you, Horace, for the honor you've brought upon us all.
Q-learning is slightly more involved than the cross-entropy method. Suppose Horace gives up his life of crime and decides he instead wants to become a food delivery fish in his local neighborhood. The only problem, Horace is a goldfish, and goldfish don't have eyelids. To avoid photic retinopathy, he's got to wear obscenely dark sunglasses. Like, the poor fella can't even see where he's going. But he takes the vision impairment because, as we saw with his dedication to Olympic diving, he'll stop at nothing to follow his dreams. With that problem, however, comes a second complication. He can't see where he's going, so he can easily run into someone's trash can if he's not careful. His first day on the job, Horace knocks over a trash can on almost every delivery, gets trash stuck to his sneakers, and inevitably tracks it and the smell all over the neighborhood and back in his 43rd story Manhattan penthouse. Not ideal for Horace. However, after days and weeks of practicing, he starts to develop a mental map of where the trash cans are most commonly found. He remembers to walk around them until, eventually, he can deliver food quickly to anyone in the neighborhood without a problem and return to unperturbed penthouse aromas.
Implementing the cross-entropy method in Q-learning in the lunar lander environment involves handing over control of the lander to an RL agent and allowing it to figure out, from scratch, which actions to take to maximize its score.
Exactly. Instead of Horace high-diving or delivering food, you can think of the RL agent as the bot pilot of the lunar lander, and we use either the cross-entropy method or Q-learning to teach the pilot how to optimally land the spacecraft. In fact, let's give a name to each of these pilots. The cross-entropy agent will be named Carl, and the Q-learning agent, Quincy.
Enough of this emotionalism. Let's get down to business. For cross-entropy, Carl, I guess. We started by selecting a reasonable target score, the score above which Carl would receive footage to use in training. Before training, you can see that Carl isn't quite adept at landing the lander. In fact, quite the opposite. He's an abysmal pilot. Meteorites do a better job landing on the moon. He doesn't pilot a lander. He pilots a crasher. Carl is so
All right. We got it, Chipper. Carl's not an expert yet. You can see here that Carl and his lander immediately plummet to the surface due to what physicists refer to as gravity. Carl will certainly not have the luxury of enjoying a 3 ice cream scoop waffle cone later on.
After several rounds of training, you can see the video footage is helping Carl do his job and avoid a poor annual performance review this upcoming fall. He manages to land the spacecraft reasonably well, but he still seems a bit hesitant.
But eventually, after several more rounds of training and forcing Carl to obsessively rewatch his good performances, Carl finally found his calling and did what he needed to do. A quick and precise landing. Way to be, Carl, minus all the poor performances that led up to that one. Given the neural network architecture we chose, Carl managed this pristine performance after about 9,000 episodes of training. Not too shabby, I guess, but how about Quincy?
Just like with Carl, Quincy also got embarrassed on his first several attempts.
You can see that Quincy occasionally indulges in high-velocity impact.
You'd think these guys were conspiring or something to destroy as many landers as possible.
After slowly developing the metaphorical muscle memory required to land the spacecraft, Quincy too learns how to be a proficient pilot and more politely introduce himself and his spacecraft to the moon. Unlike Carl, Quincy took only about 1,800 rounds of training, but he actually started sticking the landing around episode 1600. How embarrassing for Carl. I don't know about you folks, but if I had the option of choosing a taxi driver that crashed 9,000 cabs versus a driver that crashed 1,600 cabs, I'd go for the 1,600 crash cab driver every time.
I think what Downer is trying to say is that Quincy should be promoted and Carl promoted to a customer.
Something like that. But we want to remind you that cross-entropy and Q-learning are advantageous for different types of RL problems. In this particular type of problem, where the environment is relatively complex with lots of inputs, Q-learning takes the cake.
As we'll see in future robotomy episodes, there are often problems that are more suited to cross-entropy, so it'll far outperform Q-learning. There are several additional learning algorithms that we didn't even touch on here. As you can tell, we're beyond ecstatic to explore cross-entropy, Q-learning, and other dope RL training algorithms in future videos.
Speaking of ecstatic, I've got to ask, Chipper, you seem extra enthusiastic today. Why so unserious?
Oh, I'm just feeling recharged.
Well, can't argue with that.
No, I can't.
Well, anyway, when all's said and done, we've demonstrated that both cross-entropy and Q-learning can be used to navigate this lunar lander environment. In our next video, we'll compare these same algorithms by tackling a completely different OpenAI gem environment with RL. Hint, try balancing a ladder on your face.
If you enjoyed this content, please rate the video 5 stars. Also, consider delicately tapping the subscribe button if you want to stay up to date on our videos.
Although we have tons of exciting material planned for Robotomy, we're always open to new ideas and suggestions. Leave us a comment on what content you'd like to see in a Robotomy video near you.